Shall I start? All right, welcome back everyone. I am apparently meant to start, but I hope the timekeeping has not quite started yet until I have the... All right, shall I go? Okay. So welcome back everyone. In the previous talk, our technical team has introduced you to the technical concepts that have been proposed and developed by our two industrial consortia to respond to the CAIRT mission needs and requirements. In the same time, our science team has been busy to advance the scientific maturity of the mission with the particular objective to provide the evidence that the CAIRT concepts are fit for purpose and can meet the stated mission requirements, objectives, and ultimately achieve science closure. So in this remaining talk, we will make the case that comprehensive CAIRT uncertainty budgets have been established. We have compiled a database of test scenarios and test input scenes to do our performance exercise assessments. We have developed a whole array of performance assessment tools to consolidate our requirements. We have tested the robustness of these tools against independent experimental measurements and campaign data. We have then deployed and applied our performance assessment tools to confirm the achievability of our mission requirements, and ultimately developed test data sets for CAIRT impact simulations to assess the scientific and operational benefit of the mission. We have also engaged with our user community, gathered their feedback, and established a comprehensive product validation strategy for the mission implementation phase. And with that, we would claim that our mission performance has been assessed and that we have achieved a science readiness level of 5. Now, before I take you on the journey through our mission performance assessments, I would like to briefly recap the CAIRT data product and the CAIRT data processing flow. As you have seen before, we start with interferograms, and the interferograms are really associated with individual tangent points. Since we have an imaging detectors, we have interferograms on an array, on a grid, and then we feed those into our level 1 processor to retrieve basically radiance spectra. We then go on and we establish a retrieval grid that you see in blue in this image, which can be independent of the measurement grid, and we take a long track sequence of spectral radiance measurements, and we feed those into a comprehensive tomographic retrieval method to give us 2D slices, 2D pictures of atmospheric constituents and temperature along track. Now, of course, with such a picture, we have key performance requirements that are our spatial resolution and our total uncertainty, and full budgets for these have been established. We also feed these level 2A products into our level 2B processing method to basically produce our derived quantities, such as the age of air circulation diagnostic or gravity wave parameters. Now, we would claim that with that, we have based CAIRT really on a well-established data retrieval framework with an innovative tomographic application. It is not the first time that the CAIRT team, especially on experimental grounds, does tomography. However, their particular instrument, the Gloria imaging Fourier transform spectrometer, happens to look sideways out of the plane's belly pod. And as such, we cannot do a long-track tomographic retrieval. And it's for this very reason that as recently as March this year, the campaign team flew this innovative and adventurous zigzag pattern with their Halo aircraft to basically emulate this long-track viewing geometry. And very quickly after this, they were able to retrieve their first tomographic products of water vapor in this case. And I draw your attention to this particular enhancement, this feature in the UTLS around 10 kilometers of altitude. This is a filament of water vapor that has been independently confirmed with LiDAR data, concurrent LiDAR data looking vertically. And crucially also, this feature does not show up in an operational analysis, in the ECMWF analysis, which furthermore exhibits a moist bias. And we believe that this is an area where data like from a mission like CAIRT can really contribute in the future to operational weather forecasts. Now, this CAIRT flight was just one flight amongst many, and this video shows you a little bit of the excitement of these high-altitude aircraft field campaigns and stratospheric field campaigns with stratospheric balloons. But basically, the team has developed a family of instruments, starting from their Gloria AB instrument all the way to the newest member of the family, Gloria Light, which as recently as last year flew on a stratospheric balloon at an altitude of 40 kilometers across the Atlantic whilst taking fantastic measurements. So this is a timeline of the various campaigns that the team has been involved with since basically 2011. I will not have the time to take you through the details. Suffice to say that we believe with all of these campaigns, we believe that the scientific and the technical concepts that underpin the CAIRT mission are mature, have been tested, have been trialed. The campaign team also flew these campaigns with a number of scientific objectives that are well aligned with the CAIRT objectives, of course, just targeting the local scale. Again, I won't have time to take you through all of these campaigns, but you can read the many dozens of papers that the team has released based on these field campaigns. Now, of course, we don't test performance based on field data. We run performance simulations. And to run performance simulations, we need test data set. We need a representation of the truth of the geophysical state that we can evaluate something against. And for that, we have basically developed the whole climatology of atmospheric profiles that span a number of various degrees of variability. Our ERS, the extended reference scenarios that we use for the comprehensive uncertainty analysis. And in the same time, we have also, for the realistic performance assessment, created test scenes that are basically drawn from self-consistent global model simulations, such as from the WACAM-X in this case, to really test the performance on realistic data. And you see here in this image a beautiful example of an ozone field in 3 dimensions that we have used for testing our performance. This is the CAIRT mission performance evaluation framework. Please don't be taken aback, stay with me. You don't need to understand the details. The important bit is that we have many different complementary tools, synergistic tools that we can deploy for different purposes. And I will now take you step by step through some elements of this simulation world to test CAIRT performance, and by focusing on specific building blocks. The first building block is our linear performance evaluator or estimator, in short LPE. We have used the LPE tool in phase 0 to consolidate our measurement requirements and to do so iteratively. We have used it then to establish the comprehensive level 2A uncertainty budgets with detailed error propagation, and finally to assess also level 2A performance of the industrial concepts in a climatological sense. So how does this work? We start with our extended reference scenarios, these climatological database of atmospheric profiles. We feed this into our level 1B product simulator, which comprises a radiative transfer model and a parametric instrument simulator that degrades the spectra. These then go into a comprehensive uncertainty mapping exercise that follows community best practice. In particular, it's aligned with the tuner project method from a WCRP project, and this is also conceptually well aligned with ESA's quality assurance for Earth observation framework. Then we use these data out of this linear performance estimator, and we do a statistical analysis against our requirements, and we establish basically conformance against our original requirements in a statistical, in a climatological way by focusing on total uncertainty and spatial resolution. So you have seen these pictures probably before if you came to the past UCM. Since phase 0, we have consolidated our requirements that we have accounted for. We have added additional uncertainty contributor and also ingested, if you like, industrial performance. All you need to know is green is great, yellow less so, but still okay, and red and orange gets us basically into non-conformance or non-compliance with our observational requirements. And this is already one of the key results, one of the key plots of this presentation. What this shows is a comprehensive statistical climatological assessment of every single CAIRT level 2A primary constituent or product for both consortia across the full vertical range. And what it shows is that CAIRT level 2A products are compliant with our observational requirements for both concepts, except for carbon monoxide in the upper atmosphere during the nighttime. Now we can take this original parametric instrument simulator and develop something more complex, an observing system simulator, a comprehensive machine which consists of a geometry module which simulates the CAIRT orbit and the CAIRT viewing geometry. We feed into this machine a stack of top of the atmosphere limb radiant spectra. We feed those into basically the instrument model, an IFTS model, which captures the detailed instrument physics and produces the interferograms. The interferograms go into the level 1 processor, which is the operational Gloria processor, and out comes a stack of CAIRT level 1B data products. This observing system simulator is the key building block of CAIRT, of the CAIRT end-to-end performance simulator, in which it is embedded, and of which you see here a simplified flowchart. We have used CAIRT in phase A to validate our previously mentioned linear performance evaluation method, to evaluate nonlinear tomographic retrievals, basically to get a proof of concept that our processing method from level 0 to level 2 works, and then simulate the end-to-end performance of the entire system, including errors. And this is one of the examples as is output of CAIRT. So what you can see here is, again, in a long track section through, in this case, a temperature field. On the left-hand side, you see the truth. In the middle, you see the retrieved product for both consortia, and on the right-hand side, the prior knowledge, which is a key ingredient in a Bayesian-type retrieval method. The important bit here is that both concepts are able to improve significantly upon the prior knowledge, and they do so in consistent terms. So that was basically a proof of concept that even for a complex scene, the nonlinear tomographic retrieval chain really works. That was for temperature. We can do the same for other trace gas, for trace gases such as for ozone and nitric oxide in this case, and by switching on more errors. Before it was noise only, this is with additional errors. You see the retrieved products on the top and the truth on the bottom. They agree well, and we have confidence that the method works for these products and for any sort of the additional products. In addition to that, the results are consistent with our LPE framework, so we have confidence that we have really assessed our mission performance at level 2A level. And with that, I would like to hand over to my colleague Kaylee Walker from the University of Toronto, who will take you on our next steps of this performance journey towards the higher level products. Kaylee, over to you.
Thank you very much, Alex. It's my pleasure to be here to continue our discussion of the performance and science results for the CAIRT mission. Where I'm going to start is with some of our higher level products. So here we're going to talk about our gravity waves. Here we're using the scientific workbench with our full end-to-end simulator and our tomographic retrievals. Now we remember that we're retrieving gravity wave parameters using the fluctuations in the temperature profiles. So first we have to remove the background temperature to get that residual gravity wave signal, and then we put it through our two-step gravity wave processor. So first we're going to determine our wavelengths, direction and amplitude, followed by the gravity wave momentum flux and the phase speed. Now we can evaluate this against an independent truth. In this case, we're looking at the gravity wave momentum flux that's retrieved from the wind velocity perturbations in the same model. So that's the truth shown on the left. In the center is how CAIRT would see that, and then we compare to the CAIRT retrieved gravity wave momentum flux from the temperature fluctuations. And we see very good agreement here. And we can do this not only with our high top model as shown, but also with a lower top numerical weather prediction model. So this gives us confidence in how we're able to use these parameters to look at the gravity wave driving of the circulation. We've also looked at individual gravity waves. It's important to be able to track back their sources. To do this, we need to have these very accurately characterized individual waves. So to test this, what I'm showing on the right-hand side is going down in altitude. This is gravity wave momentum flux over a winter, and we can see those gravity waves localizing in the areas of their sources. And then we look and compare these to where they're coming from, and it makes sense because these are the mountainous regions. We've also done a full uncertainty analysis of our gravity wave parameters that we've retrieved. This is using a Monte Carlo simulation setup, and you can see across the top that very good performance for all of these different parameters. So we've shown that we have sufficiently accurate parameters so that we can look at the sources of these individual gravity waves. Moving on. We've done work with our FAST Level 2 simulator, another part of our scientific workbench, and we use this to generate data sets that we can use not only for assessment, but also for scientific studies, which I'll tell you about later. So here we're going to focus on age of air. So what we've generated are time series of long-lived tracers. On the top is sulfur hexafluoride, the classical molecule that we use to determine age of air, and on the bottom, another one, CFC12. What we're doing here is we're going to average around in longitude to create zonal means, and we'll use that zonal mean of SF6 in the standard method to calculate the age of error. Then we do correlations between that age of error and the long-lived tracer zonal means, and we do this for a multitude of different tracers using these correlations to get the 3D age of error from CAIRT. Now, again, we'll assess this against an independent truth. So in the back, I'm showing the age of error that's retrieved from our independent truth, the clock tracer in our model, and on top are the CAIRT retrieved ages of error. If we look over a day, these are the zonal means, shown on the left, the retrieved age of error, and on the right, the propagated uncertainties. If we look at the differences to that independent truth, that's shown below, we can see this in the zonal mean sense, and we've also assessed the combined error against the truth. And we see very good agreement between the propagated uncertainty and that error, combined error against the truth. So this gives us very good confidence in the utility of our age of error products. We've also done an experiment where we've used results from a high-altitude balloon campaign and Gloria measurements, comparing the standard method against our new correlation method, and we can see the significant decrease in the uncertainty that comes with using this correlation method. And the importance in this is the smaller that uncertainty is, the better that we're able to discern between different model simulations. Shown here, this is the Basco-E model with 3 different meteorological reanalyses, and we can see how that CAIRT retrieved age of error can discern between them. So this is really important to be able to constrain and assess models to have these low uncertainties. Now, enough about performance, that was wonderful, but I really want to tell you about some of the exciting science and impact studies that we've been doing during phase A. There's a couple that are still ongoing, one looking at using CAIRT to improve model representativeness, and another on volcanic ash, which I won't touch. But I am going to tell you about coupling between space and the middle atmosphere via gravity waves, the use of CAIRT data in the upper troposphere and lower stratosphere through data assimilation, and then a case study looking at geoengineering through stratospheric aerosol injection. So where we're going to start is the northern hemisphere winter. The polar vortex, which can be disturbed by wave activity, leading to a sudden stratospheric warming. Now, the vortex can reform after this, and as it reforms, the reactive nitrogen oxides, that NOI, can be transported down from the upper atmosphere to lower atmospheres and into the stratosphere, causing this ozone depletion or radiative cooling. Now, how far down that NOI gets really depends on the strength of the gravity waves interacting with the vortex as it reforms. I'm showing here in the blue arrows the circulation, poleward and downward. And you can see as the strength of the gravity waves increase, that circulation moves to lower altitudes and to higher latitudes. Now, looking at the weak and the strong cases, we see very little or none of the NOI getting down into the vortex. It's the moderate case of the gravity waves that really gives us that perfect storm where we get the transport of NOI down into the stratosphere. So to be able to model this correctly, we really need to get the gravity waves right. So what we've done is we've assessed the possibilities of looking in these different scenarios for the gravity wave momentum flux and the drag. So shown on the left is the case for the weak gravity waves, on the right, the moderate ones. We can see that increase in the gravity wave momentum flux as the strength of the waves increases. And we can also see the impact of the gravity wave drag changing. So it's only interacting at the highest altitudes for the weak gravity waves and extends to much lower in the case of the moderate gravity waves. So these direct observations are really important information to allow us to model these gravity waves correctly. We've also been able to look at this situation from the standpoint of the NOI. So here we're showing averages of the NOI throughout the polar vortex. And this is a time series with altitude. And we're using 2 cases, one with weak gravity waves and one with strong gravity waves. The arrows and the dashed lines show the extent to how far down that descent occurs. And we can see in the colors the different amounts of NOI that is transported to those lower altitudes. And we can see the agreement with what we talked about earlier. And I'll remind you that the NOI is on a log scale. We can compare these to our CAIRT simulated measurements, showing here the case for the weak gravity waves, and we can see excellent agreement. So this really gives us confidence that we can use CAIRT measurements of NOI to be able to diagnose the impact of wave driving on the descent into the vortex. The second science study that I'd really like to focus on is looking at the upper troposphere and lower stratosphere. And this is an important region for the radiative balance of the Earth. So we're looking at a data assimilation experiment here. We're conducting an observing system simulation experiment, an OSSI, where we're going to assimilate CAIRT, ozone, and water vapor to see their impact. So to do this, we're going to need two different models. First, we're going to use a model that's our truth. This is our nature run. We're using the CAMS model. And then we're going to use the BASCO-E model in three different ways. First, we didn't assimilate anything. This is our control run. Next, we've assimilated measurements from the microwave limb sounder. This is the current gold standard for this type of simulation. And next, what happens when we assimilate simulated measurements from CAIRT? We see the definite improvement. We can evaluate this by comparing each of those BASCO-E runs against the nature run, and we can see the definite improvement that comes with data assimilation of these two molecules. And we can see quite comparable results between the current gold standard of MLS and CAIRT. It's recently been highlighted in the ECMWF Spring newsletter, the importance of having measurements such as CAIRT to give us the high resolution and that important data set into the data assimilation models. So this is a definite important application of our CAIRT data. The last study that I'd like to tell you about involves potential geoengineering action to moderate solar radiation. Here we're going to focus strictly on the case where we're increasing stratospheric aerosols. Now this is a more and more probable scenario that we're going to be facing in the near future. It's a case where when we think about injecting stratospheric aerosol, that does have a radiative effect, but it can also have other effects potentially. And it's the concern for these different effects that can happen in the stratosphere and other levels in the atmosphere that have caused a number of international organizations to study this. One such study comes from the United Nations, and here they indicated that we need to be concerned at looking at potential risks and uncertainties of doing this, as we only have one atmosphere. And they also highlight the need to look at rocket launches or maybe spacecraft re-entry as places where there's very little regulation but can have a big impact. So what we did in the CAIRT study is that we were looking at how CAIRT could contribute. So the simulations were done by considering relatively small injections of sulfur dioxide. These are of the order of what can be done in the next decade or even sooner. So the two injections that were done are shown on the right-hand side, showing the altitude and the latitude. On the left-hand side, we're looking at 25 kilometers, and this shows the simulated CAIRT measurements. When we look in the vertical and compare against the input truth, we can see to the small levels, that half-ton spread over a 100 by 100 kilometer area, that CAIRT would be able to detect of this type of potential injection. And not only will CAIRT be able to give us insight into the sulfur dioxide, it also provides lots of other parameters and measurements that will be very critical to understanding what's happening. So CAIRT can really be our eyes in the sky in trying to understand the potential impacts of this type of activity. Now, all of this hinges on having really good data. So one thing we need to consider is our validation study, as was mentioned earlier. We've got 3 different components that are involved in this. Dedicated airborne campaigns, both aircraft and high-altitude balloon, using prototype instrument for CAIRT. Making sure that we're leveraging existing networks, ground-based as well as balloon-borne, for remote sensing and in-situ measurements, as well as using data assimilation, not only assimilating our CAIRT measurements and comparing them, but also looking at the results of assimilation to compare to CAIRT. Now, in looking at the context in which CAIRT would fly as the Earth Explorer 11 mission, We have listed here a number of the LIM missions that are currently in operation or are in planning and development. You'll notice that we have a nice suite of heritage missions, some of which have known end dates, some which may end earlier. This loss of these heritage missions really decreases our capacity for detecting change and predicting what's going to happen in our rapidly changing climate. So what I'd like to do is I'd like to have you cast your mind 2 years in the future. And now we're going to look at only the missions that at that time will be in baseline operations or in planning. And we have a significantly different landscape. All of these missions that are planned are highly complementary to what CAIRT would give us, but they cannot replace our unique measurements. They focus on a narrower range. They also cannot address our science questions. 3 of our science objectives could not be achieved at all with these measurements, and the other 2 only in part. So it's really important to have these measurements to do the new and exciting science that we want to do with CAIRT. The other thing to think about in this context is the synergies with the nadir measurements. There's lots of possibilities here. We've highlighted the ones with MEDOP, but these can be applied to a number of different molecules, and it really allowing us to extend what CAIRT can do to lower altitudes. The applications and the user interest in our data are strong. In terms of what our data can bring to model intercomparison projects, we not only provide data for assessment, we also provide critical inputs for climate forcings across a number of different areas which are of importance in this. We also address a wide international user community. The World Climate Research Program has been mentioned. 2 of its 6 core research projects are very excited about the data that's coming from CAIRT. And one of their lighthouse activities has particularly highlighted some of our particulate measurements and aerosols. When we go to the higher altitudes, the SCOSTAP activity of the International Science Council is really excited for the step change that will come for the CAIRT measurements in looking in their region of the atmosphere. During Phase A, we've reached out to our user community and gotten feedback on what people are interested in doing. You can see there's a wide range of interest. They highlighted the importance and excitement in high-resolution 3D data, how they can use these data to constrain models, and how they can employ these newly developed techniques. So we have a user community that is ready and waiting for CAIRT data with these wide range of scientific interests and applications. So as we bring our hour-and-a-half presentation to a close, I will highlight why we believe that CAIRT should be chosen as the Earth Explorer 11 mission. First, CAIRT is relevant. Our measurements target the middle atmosphere, a key region for the Earth system understanding and prediction. Next, it is unique. CAIRT provides a comprehensive view of this region, combining composition, circulation, and waves, including the first measurements to resolve gravity wave momentum flux. CAIRT is innovative. It will be the first hyperspectral limb sounder in space, providing new high-resolution 3D view of our changing atmosphere. It is complementary. CAIRT significantly increases our Earth observation capabilities by providing atmospheric information with high vertical resolution, and it exploits existing synergies with nadir view sensors. CAIRT is timely. As we respond to a rapidly changing climate, there is an urgent need for new measurements to quantify and understand these changes as they occur. It is mature. We have built CAIRT on strong scientific and technical heritage, coupled with solid performance experience. And finally, CAIRT is useful. It provides unique observations that directly address science and prediction needs as expressed by the community and to benefit society. So to close, CAIRT will bring a new age of exploration with innovative limb imaging infrared tomography and exciting new science and applications. So I thank you very much, and I will hand over to our ESA colleagues for the programmatics.
So
Thank you, Kayleen. That was wonderful. So we have heard in the last 1.5 to 2 hours the excellent presentations by the CAIRT science and technical teams. They have been walking us through everything they've done in the phase A, even before, of the last few years, in consolidating their science and basically also consolidating the technical concepts, and they're also looking into the performance assessments. So this is all an extremely important element of what we will be discussing during the coming, during today and also after this presentation. Another important element is, of course, also where do they stand with respect to the requirements that we have set to them after phase A in order to go forward into implementation. And this is the programmatics part. And I'll be presenting this together with my colleague Bernardo Canichero, who is sitting here in the back. So I will be addressing the technical part, and Bernardo will be addressing the technical part. So first on the scientific maturity. So the CAIRT phase A science and feasibility studies activities, as they've been documented in the excellent report, and I invite you all to go through the report. It's a lot of information. It's very good information. They have basically demonstrated together with today's presentations, the Science 1, the Science 2, that they have been, that they have quantified the scientific performance based on the validated tools that they have been developing, and they have scientifically justified test scenarios allowing the rigorous computation of uncertainties. This is enormously important for us, that we have also always an uncertainty estimate to the science that they will be providing. They have also established a draft calibration and product validation strategy. This is in particular important when we go forward. Then they have demonstrated the high interest in the mission by the scientific community, and this is what also Katie has just shown wonderfully in her final slides. And they have provided the first evaluation of simulated and measured data in applications. We've seen this as well with the wonderful simulations that have been shown and the animations that have been there. So on this basis, we can judge that the candidate mission team has been successfully demonstrated what we call mission performance, and has assembled the required evidence to justify the scientific maturity, which we call scientific readiness level 5, which is what they need to achieve after the phase A. So as a summary, we can say that the phase A objective to mature the mission science and to proceed into an implementation phase has been achieved. We have also asked them to assess the critical areas and risks, and the CAIRT MAG, the campaign and the study teams consider that there is a low scientific risk, and they base this on the established retrieval framework that they're having in place and on the existing and heritage instruments that they've also demonstrated and shown during the presentation. They've also shown that there's a full traceability of the science requirements, of the objectives to broader challenges, and they have been all vetted by the scientific community. So overall, we consider, or they consider, that there is a low scientific risk for the mission in case it will be going forward. We are also asking them to provide a scientific roadmap, so looking forward, so going ahead, in order to show us how they would mature towards the next, what we call scientific readiness levels. And they will be focusing on a number of key activities. So on the one hand side, it's the maturization of the retrieval algorithms, and they will do this with an emphasis on optimization of speed of the tomographic inversion, including the non-local LTE, or non-local thermal equilibrium physics, and the system energy distribution function retrieval approach. So they will be refined in order also to increase the performance of the retrievals. They will be also exploring theoretical and laboratory spectroscopic studies, and you can imagine that with all the trace gases and elements that they will be retrieving, spectroscopy is at the core of what they're doing. They will also investigate this in order to reduce uncertainties that are coming along with the spectroscopy. There's also the aim to adapt an existing imaging Fourier transform spectrometer as an instrument that can really serve as an airborne, potentially airborne demonstrator for the CAIRT mission. And they're also investigating operational updates through data assimilation, AI and machine learning are here the key elements. So with this, we consider that the mission is mature to go forward, and I will hand over to Bernardo for the technical elements.
Thank you, Torsten. Good morning, everybody. I will be concluding this morning's session, providing you with a summary of the technical programmatics for the mission. And to start with, I would like to introduce to you an overview of key features of the Phase A. The first one, as you've seen in the technical presentation, the Phase A preparatory activities have defined technically feasible system concepts, which have the capability of fulfilling CAIRT mission objectives. In addition, the Phase A has also identified items that require technology pre-development due to the technological maturity or the relevance for the technical or programmatic feasibility of the mission. And as well, the Phase A has identified performance items, design drivers, that also will require close attention during the mission implementation. With these two elements together, the Phase A has initiated technology pre-development activities to mitigate the risk, but also to progress towards TRL 5 that will be achieved at the end of Phase B1. In addition, and this is also very important, the Phase A preparatory activities have established a thorough and structured pre-development plan, which is fully aligned with the Phase B2 CD development strategy in order to enhance the mission maturity and also to allow the achievement of the requirement of the TRL 5 on critical elements at the end of the Phase B1. The following slides shows an overview of key elements of the technical maturity, critical areas, and risk for the mission. And particularly for the payload, as you've also seen during the presentation, the MCT, the mercury cadmium telluride detector array, the interferometer, the cryogenics, and to the less extent, the diachronic beam splitter and its coating are considered critical items due to the technical maturity or its relevance for the feasibility of the mission. It is, however, very important to state, as you've seen during the technical presentation, that CAIRT payload benefits from large heritage on particularly these key items and these critical items, and particularly, as you've seen in the technical presentation, in terms of the interferometers, the heritage from TANSO Forum missions, for detectors, for instance, the MTGIRS detector technologies, and for cryogenics as well. Finally, in terms of items or performance that require close attention, also as mentioned in the technical presentation, the noise equivalent spectral radiance and the radiometric additive uncertainty for concept B, and the vertical crosstalk and straight light are items that require attention. Moving into the satellite and the platform, and starting with the platform, CAIRT is based on ongoing developments within the Copernicus Sentinel expansion mission that, of course, require their adaptations in order to meet the specific mission needs. These adaptations do not introduce any specific risk for the mission. CAIRT is also compatible with Vega C launch mass and also in terms of the fairing volume, and there are sufficient mass and volume margins to accommodate potential evolutions in the design during later phases. No risk have identified neither on the compatibility with Vega C. Finally, as in every limb sounder mission, accurate pointing is a key performance requirement, very important for the mission, as explained also during the technical presentation, and in particular the pointing knowledge and the stability. Pointing, of course, is also needs to be a key focus through the design process, but as also stated in the technical presentation, the performance is similar to other missions from ESA. During the Phase A, technology pre-developments on all the critical items that I've referred before, the detector arrays, interferometer, the cryostats, and the cryogenics, and the diachronic beam splitters and coating, have been initiated with the aim of progressing to the TRL 5 that will be achieved at the end of Phase B1. And, of course, during the Phase B1, pre-developments of these units will be as well a focus. It is worth mentioning, as also explained in the technical presentation, the effort done on CAIRT, particularly on the detector arrays, for which there's been pre-developments with all three suppliers, European suppliers, and also the interferometer and the effort as well on the cryogenics. Expanding a little bit the picture of all the Phase A B1 pre-development plan, you can see here a block diagram of the simplified block diagram, of course, of the main elements of the payload of CAIRT. And in orange, you can see the critical items under pre-development initiated in the phase A, and that will continue during the phase A1, as we've mentioned, interferometer, detectors, the cryogenic part, and the dichroics. In orange, you can see non-critical items under pre-development in phase A and in phase B1 that will increase the TRL and or retire risk during the implementation. And in green, elements, well, for instance, in yellow, the pointing unit, back telescope, or the proximity electronics of the detectors. In green, you see other elements that they are considered mature enough and not requiring a particular pre-development during the phase B1. In summary, the results of the phase A pre-developments and the proposed phase A1 technology pre-development plan are considered suitable to retard the identified risks, confirm the performance, and reach the target TRL5 at the end of phase B1 on critical elements. In terms of the development approach, CAIRT follow standard phase development with phase B2, CD, E1, and of course, phase B1. Both industrial consortia have proposed parallel development activities on the instrument, platform, and satellite level. In terms of the model philosophy, at platform and satellite level, it will follow the standard proto-flight model approach that will be used for thermal, mechanical, and electromagnetic compatibility qualification. It's no expectation to use, actually more than no expectation, there will be no structural model or structural thermal models at platform level. For payload, the approach proposed is to use engineering models or engineering qualification models for critical elements, and engineering models and going directly to flight model or proto-flight model for other payload equipment. CAIRT schedule, as you may imagine, is driven by the instrument development, and in particular by the development of the focal plane assembly, which is on the critical path. Assuming a kickoff of the phase B2 CD E1 in the first quarter of 2028, and taking into account the appropriate schedule margins, it is considered that a launch in the 2033-2034 timeframe is compatible with the proposed development plan. CAIRT addresses the relevant ECSS standards for the Earth Explorer program, complies with the use of European launchers. There's no ITU regulation issues. CAIRT, as shown before, will re-enter in a controlled manner. And it is worth to highlight that the application of the new ESA space debris regulation, which I would like to remind that it was not at effect at the time of the Explorer 11 call, will require additional adaptations to the satellite design and also additional analysis. And in conclusion, CAIRT has reached the required scientific readiness level and the technical maturity at the end of phase A. It benefits from heritage on the critical items, particularly in the interferometer and the detector and the cryogenics. And finally, the results and achievements of the phase A pre-developments and the successful outcome of the planned pre-developments in phase B1 will retard the risk, confirm performance, and reach the target TRL5 on critical items at the end of phase B1. So to conclude, it is considered that CAIRT is sufficiently mature for selection and as ESA's Earth Explorer 11. And then one extremely important slide is the acknowledgement. As you've seen during the whole presentation, there's been a huge effort and commitment by the scientific teams, the MAC, the teams that are conducting the campaigns, the consortiums in industry, my ESA colleagues, the teams are conducting the end-to-end performance simulator. It has been extremely large effort as I hope you can recognize in the excellent presentation. And I would like to thank you for your commitment and for pushing the science and technology ahead in order to make sure that, as it was mentioned by Rune, this is in the Explorer 11 world-leading missions as they are. So thank you very much, and of course, thank you all here to you that come to Prague, and also the ones that are remotely. Yeah. I shall not introduce.
So we have a moment of transition where the MAG and the technical teams will be coming on stage in order to answer all of your questions. The way it works is that Alex, as the mission scientist, will be moderating the discussions, taking your questions. We also have questions online that we will be taking. The idea is that we first take the questions in the room and then reserve some time at the end of the discussion sessions or whenever we run out of steam in the room. And Alex, I hand over to you for discussions, and again, thanks to the MAG for coming on the stage and the technical team.
I take the questions. Okay. All right. Thank you very much, Torsten. So thank you very much to everyone and to all our colleagues for all the presentations. And with that, I would like to get the Q&A session started and open the floor for your first question. I see one there in the background. Yes, please. Please state your name and affiliation, and then we'll redirect it to the MAG. Sorry.
Sorry. Yeah, so thank you very much for the presentation. My name is Amanda Maycock. I'm the lead of the World Climate Research Programme APARC activity that was mentioned in the presentation. We have a community of more than 700 researchers worldwide who would directly use CAIRT data in their work. So my question is actually about climate modelling, because I'm actually a climate modeller. So we know that the models that are used to project future climate that inform IPCC have a first-order dependence on gravity wave drag parameterizations. And it was mentioned in the presentations, these are a long-standing source of uncertainty. They directly affect regional climate change projections, particularly in the extratropics over the coming decades. What will CAIRT do compared to kind of past and current capabilities to enable us to try and improve those model simulations and reduce uncertainties in our climate projections? Thank you.
Thank you very much. Okay, I hand over to Peter to start the answering of this question. We need a microphone as well, please.
Yeah, so thanks, Amanda, for the question. Of course, you have seen in the simulations that we can really take it down source by source, and that is one of the shortcomings at the moment, that you have to put it all together in improving, but then we have also the phase speeds, we have at a different altitude, and we can see all kinds of propagation features which we all can use to confine better climate models.
So one of the important issues with climate modelling, especially climate change relating to the stratosphere and impacts below, is the diversity of particular projections and different models. So under climate change, we see, as far as the polar vortex is concerned, and we saw polar vortex is very important when it comes to impacts in circulation lower down. Different models have completely different responses. So by employing observations, better observations in gravity waves, we can use those to improve parameterizations in those models, and we know that that will have first-order impact on the polar vortex, especially higher up. And it's at those higher altitudes that things like sudden stratospheric warmings are known to be preconditioned by things such as wave forcing. So that will be a first-order response in modelling with regard to gravity waves. And my name is Scott Osprey. I'm National Centre for Atmospheric Science at the University of Oxford. Thank you.
Thank you, Scott. I'm ready to take the next question. Oh, over there, I think, and then next over to you. Thank you.
Good morning. I'm Aurélien Poglagen, a researcher at CNRS, Laboratoire de Météorologie Dynamique in Paris, France. And my question is related to extreme perturbations of the stratospheric aerosol layer. In particular, following the 2020 Australian fires, we have seen very specific behavior of stratospheric aerosol plumes, which remain confined for months within vortices of hundreds of kilometer diameter. This has very important implications for the dispersion of the aerosols and then ozone loss and climate impacts. And we have still very big scientific questions regarding the dynamics of those structures and having information about their 3D organization would really help. So my question is, will CAIRT be able to detect such events if they happen, and they will happen probably with the increased occurrence of wildfire, extreme wildfire with climate change? And also, can we, with CAIRT observation, characterize the 3D structure of dynamics, so temperature, aerosols, also water vapor, ozone, in those extremely perturbed conditions?
Thank you very much for your question. I suggest to start with Sophie.
Yes, thank you for the question. I'm Sophie Godin-Beckman from CNRS, and indeed this new phenomenon are very interesting to study. With the CAIRT characteristics in terms of spatial resolution and vertical resolution, it will be indeed possible to resolve these features and also to detect the gases and the aerosol that will be present in these features, such as the carbon monoxide, ozone, water vapor, and also the various gases like peroxyacetyl oxide, and also other combustion products that are present in these features, and also the temperature dipole that are present in these phenomena. So I think it will be really the mission CAIRT is really well thought to detect such events, and also to look at the various pathways that these events can happen in terms of injection by pyrocumulonimbus or by warm conveyor belt, because we will have a very detailed view of the tropopause.
Thank you very much, Sophie. I saw a question earlier here on my right-hand side. Yes, in front. Thank you.
Hello, my name is Linda Megner. I'm from Stockholm University, where we're working actually on quite a lot of the things that CAIRT will hopefully be able to do. One thing, I actually have two questions, if that's allowed. The first one regards whether I think in a few years now, and certainly with CAIRT is up, there will be more material in the atmosphere from ablated re-entry satellites than from natural meteors as we have today. We're about to go past the mass from natural meteors because we have so many satellite launches. So my question there is, and we don't really know what this material does to the atmosphere. So a mission that could actually see re-entries of satellites in some way, either spectrally or directly from the emission of the particles, thermal emission, that would be super useful. So can CAIRT do that, is my first question. And shall I take the second directly, or it's a little bit... I'll say the second. The second is regarding gravity waves, and I think one thing there that we're sort of realizing now is that we don't always have gravity waves that are launched all the way from the surface up to the top of the atmosphere, but we have these secondary gravity waves, which I don't think you mentioned so much about. So I just wonder, will you be able to distinguish in between secondary and first gravity waves?
Okay, thank you very much for your question. We suggest we start with Martin.
Yeah, thank you. Martin Chipperfield from the University of Leeds. Yeah, thank you for the question. I'd be happy to answer this. And you're right, this is a very important and increasing topic. In fact, 2 years ago in Bucharest, this topic was just sort of becoming to the fore. And we had a similar discussion. And yeah, the increasing amount of ablating re-entry satellites, largely aluminium burning in the atmosphere. And in fact, we've got a backup slide. If we can show the backup slide that I'll talk to. Yeah, so the big advantage of a infrared spectrometer, for example, is given a new topic to address, you can look at spectra and test new retrievals. And so in following the question at Bucharest, the issue rising there, Mikhail Hofner, who's in the audience, has done test retrievals on alumina, Al2O3, using parameters generated recently by a paper by Maloney from NOAA, who are sort of leading lots of work in this area. And basically, the short answer is yes, for the projected amounts of alumina that have been modeled to get to a BE in the atmosphere by, say, 2040, using increasing ablation rates. CAIRT can well see it. The left-hand plot illustrates what it would look like in the spectrum. It gives a signal about 40 times larger than polar mesospheric clouds, which you can see. So basically, the simple answer is yes, we've checked CAIRT for this new topic, and we can observe alumina at the levels expected. So we'll observe particles, check their impact, and look for chemical impacts, for example, on heterogeneous chemistry. So, yeah.
Thank you, and maybe to Peter for the topic of the secondary gravity waves.
So, I mean, you have seen the ray tracing, so we can take the lower atmosphere sources up. We can go from higher down and see. And if we see breaking from the lower sources, and on the other hand, that we have a source region, then we have a good indication. And of course, CAIRT is not only able to see one gravity wave per volume, but hopefully you can actually see the coexistence of the going and the coming ones.
All right, next question over there, perhaps. Mm-hmm. All right. Yeah. 1 second first over here on my right. Thank you.
Hello, I'm Ross Salowich from the University of Maryland. On behalf of the middle atmosphere chemistry and transport community in the US and my colleagues, I'm one of the few to be able to travel over here. We're very excited about the possibility of this mission being selected, and in particular with the lack of future observations from satellites that are very aged. My question is about ozone layer recovery. As was stated earlier by Alex, the ozone recovery is slower than expected. And my question is, can you provide some more detail from both the dynamical perspective and the chemical perspective, perhaps gas is not yet regulated by the Montreal Protocol, how the CAIRT observations can be used to improve our knowledge of the causes of the slower than expected recovery of the ozone layer?
Thank you, and back to Martin again.
Okay, yeah, thanks. So yeah, it's a complicated and sort of surprising issue, the fact that in different regions, the ozone layer is not recovering directly in response to decreasing chlorine in line with the Montreal Protocol. So the regions of interest are sort of the northern hemisphere, lower stratosphere, and there's a clear interhemispheric difference between what's happening in the northern hemisphere and southern hemisphere, which seems to be related to dynamics, and we have some information from past satellites. But CAIRT will give this much more complete, detailed picture of dynamics and the apparent hemispheric asymmetry of the Breuer-Dobson circulation leading to these different recovery rates through transport, and even in the Arctic, which is obviously very different to the Antarctic. So I think the transport side is very well covered. For chemistry, CAIRT has complete coverage of the NOI species, which are related to heterogeneous chemistry and possible impacts of different aerosols. For example, wildfire smoke in 2020 fires is mainly organic aerosol, will activate chlorine in different ways. There's an issue of why ozone was low in the southern hemisphere after the Australian wildfires. Was it transport from the heating rates for aerosols, or was it chemistry? So through the complete coverage of NOI and chlorine nitrate, and as secondary objectives, CLO and HOCl, we'll get quite a bit of information about heterogeneous processing on different types of aerosols, which may be affecting that, and the hunger water vapor, we should mention as well. Yeah, and there's like, we'll rely on complementary data from surface networks for emissions of controlled gases and so on. So they'll be all fed into models and data assimilation systems in Synergy. So I think CAIRT will add a lot to the picture and things that only CAIRT can do in situ in place in the middle atmosphere. Okay.
So maybe I can add one note specifically to your question, Ross. One of the additional short-lived chlorine components that are suspected to affect chemically the delayed ozone recovery is dichloromethane, for example, and we don't have that as a primary species on the list for CAIRT, but it's a similar story like with the aluminium oxide. We know the spectral signatures are there, and my colleagues, for example, Søren Johansson with the Gloria instrument very recently was able to detect that on a recent campaign, so there is definitely the possibility that we can get that also from CAIRT.
I saw one over there. There's a number of questions. I don't know who was first, so I believe you already have the mic. Thank you very much.
Good morning. So my name is Philippe Chambon. I work at Météo France, the French National Weather Service, where we do forecast of weather, but we do also atmospheric composition forecasts. And I had a question on the complementarity with other missions that you have mentioned. So this morning you have well explained the complementarity that you would get with YASI-NG. I was wondering if you could elaborate as well on the complementarity that you would derive with Miliosat third generation with the IRS. At Météo France, we have high expectations of impact of MTG-IRS for ozone forecasts, for instance. And we know that by the time Earth Explorer 11 will be launched, there will be almost, I think, a geo-ring of those instruments. So I would be very interested in learning more about the complementarity with geos as well.
So who wants to start? Björn Martin, and then maybe over to Pierre.
Yeah, thanks. I will start with a very general message that with the lack of future LIMP sounding missions, the possibility of CAIRT is really to add a new dimension to the other sounders. So therefore, any potential impact by just having data that are totally complementary that we have from other satellites is potentially very useful, even though we have not investigated that in detail during these phase A studies here. Any of my colleagues wanting to add?
Piera?
Piera Raspolini from IFAC CNR. Especially during phase 0, we have also verified that the complementarity between CAIRT and YASI-NG and also Sentinel-5 could provide an added values because could improve the performances in the UTLS that is known to be a very critical region to study from space, and of course, especially for ozone, but also for other species and also for methane, we have seen that the improvements coming from the information on the stratosphere coming from the LIMB observation, from CAIRT observation, helps to improve nadir observation also in the very low layers of the stratosphere. And I think this is the potentialities of synergies are very important and should be emphasized and used, exploited.
Okay, thank you very much. Next question. Yeah, over there. Thank you.
Hi, thank you. Hello, this is Marta Ábalos from Universidad Complutense de Madrid in Spain. And well, I'm currently leading or co-lead of the climate chapter of the ozone assessment report that will be published in 2026. And this is the chapter of this report that deals with the coupling between ozone and climate. So it deals with the effects of changes in stratospheric ozone and composition on surface climate, so not only on the long-term trends, but also subseasonal variability that is more and more relevant. And then it also deals with how the changes that we expect in stratospheric circulation will affect the recovery of the ozone layer. So in this last point, we have seen in the presentations before that that there's a very large uncertainty in how the stratospheric circulation is changing. So this overturning circulation or Burrow-Dobson circulation, we cannot constrain it well with the observations we have so far, and we have seen in Kaylee's presentation some really nice constraints for the mean age, and I was surprised to find, or at least this is what I understood, that the mission is planning to output a product that is specifically directly the age of air. So my question is about this this output, and how is this CAIRT new, are these new CAIRT measurements different from what we have up to now, and how can that improve our understanding of how the stratosphere is changing and is expected to change in the future?
Thank you very much. Kaylee or Martin, perhaps? Okay. Quentin?
Yeah. Thanks very much. Indeed, age of air is a level 2B derived product derived from long-lived trace gases, in particular sulfur hexafluoride. Sulfur hexafluoride has also already been used from the MIPAS instrument, and then in the early 2000s, and then from in situ observations. But the uncertainty of from SF6 alone is not sufficient to derive the required total uncertainty of less than half a year at the small spatial scales. So we use the ability of CAIRT to derive a large number of long-lived trace gases at this high spatial resolution, and as Kaylee explains that, through the correlation between these long-lived trace gases, we can come up with a derived product that can directly be compared to what has been done, for example, with MIPAS before. And the new imaging technology, together with the tomographic retrievals, allows us now to do that at a much smaller scale.
I see a hand over there, just, yeah. Thank you.
Thank you. My name is Daan Hubert. I work at the Royal Belgian Institute for Space Aeronomy. I am a science lead of ESA's Ozone CCI project, so dealing with the generation of ECV products. I have been part of the ozone assessments on changes in stratospheric ozone, and just recently I have the responsibility to look into tropospheric ozone changes as well. This is an IGAC project. My question is about middle atmosphere and CAIRT, but actually a bit lower down. You are measuring middle atmosphere and you have a good constraint, hopefully in UTLS, so you can have a very good, hopefully, stratospheric column, which makes CAIRT ideal to look at tropospheric columns. So this is important for air quality, also for the sensitivity to climate, the climate sensitivity. So my question is, how, well, actually not a question, I hope that you can measure long enough to look at long-term changes. So I heard about a mission of 5 years extended to 10 years. Is there a possibility to add the 200 kilograms that is still of fuel to have another 5 years? Because as far as it stands, it will be the only mission in the air that will be able to give us these data in the coming 10 years.
I think I'll hand that to the technical team.
Thank you, Alice, CAT Study Manager for ESA. So indeed, this mission is advertised as 5-year nominal lifetime, but it is based on platform from Copernicus. These platforms are very reliable. We're targeting typically reliability over 0.9 for the nominal lifetime, and we are taking on board enough fuel and other items to make sure that the mission can last up to 10 years as long as all of the systems are nominal. And at the end of the time, when the systems are starting to not be nominal, then the mission is deorbited. But yes, there are very good chances to extend the lifetime.
Thank you, Alizé. Next question. Well, maybe there in the back and then here in the front. There's a number in the back.
Hello, Petr Šácha here from Charles University, Prague. Thank you very much for giving together this excellent proposal for this exciting mission. I would like to ask a question about brew-adoption circulation, so kind of following on what Marta already asked. So brew-adoption circulation and its changes are dominating the models or projected changes of the middle atmosphere in climate models. And we are struggling to constrain those changes with observations. And besides of this excellent H-of-R data product that you propose, I would like to ask about the methodologies that were originally developed for MyPass data. And based on the tracer distributions in MyPass data, there were methodologies how to derive estimates of actual Lagrangian circulations and potentially also mixing. So can we then expect those methodologies to be applicable to CAIRT data, and can those methodologies be potentially like enhanced in their performance based on CAIRT data? Thank you very much.
Yeah, so Bernd Funke from the Institute of Astrophysics in Spain. So indeed, this is a very nice approach which goes in synergy to the direct measurements of H-of-R. So this cannot be a level 2A product because it requires level 3 analysis. And indeed, there are plans to look in this in very much detail because CAIRT will provide all the trace gases required to do such an analysis. So basically, we're talking here about the CFCs, about SF6. We are also talking about methane CO to extend to higher altitudes even. And this is definitely on the route for the future to look into these developments.
Thank you, Bernd. I saw a question over here and then back there again. First here, perhaps. Yes, thank you.
Thank you. Lukas Krasowska, Stockholm University. So you have showed that CAIRT will reveal fine spatial structures in many tracers in 3D. And also it seems that the swath width of the instrument would be quite large, like 400 kilometers you have showed, which would result in generally very high volumes of observed data. So the question is, will that allow possibly for repeated observations of certain air masses? Because, well, that would be very interesting in really tracing possibly the time development of the fine scale spatial structures. And I'm asking because I have tried to do this with other instruments, and really what seems to be the key in this repeated observation is just really the large volume of observation. And well, if you haven't thought about this aspect, then maybe more generally, like how do you intend to leverage the high resolution and the 3D nature in the tracer structure?
Do you want to go? Peter again.
Okay. Yeah, so we have checked it. You will find it in the report. And actually, yes, it really depends on the width of the track width. And 300 kilometer would be enough, and 400 even better. And as you say, if we don't have a large track width, that wouldn't help. And what also, if you have only one track, you can't do it. As you say, for mixing it's great, for chemistry it's great. And other things are, of course, that we can go to lower altitudes. Michael has done some studies that you get much more cloud-free observations.
Yeah, over there.
Thank you. Yes, Amanda Maycock from the University of Leeds. So I'm going to ask a question about stratospheric aerosol injection that was mentioned by Kaylee. So this is obviously a topic that's becoming of greater prominence. I recently chaired a discussion at a UN panel event with scientists speaking to policymakers about SRM, and that was about observational capabilities. I also lead the chapter for the next ozone assessment report on stratospheric aerosol injection, and we're currently writing that. And one of the key issues is that at the moment, much of the evidence we have about the potential risks of SRM is based on climate models, which have imperfect representations of many of the key aerosol processes. You mentioned that CAIRT will have the capability to do the sort of full sulfur budget and look at all those terms. Of course, we have no idea now about, on the timescales of CAIRT, whether somebody might think to do SAI or not, and we don't know whether there would be a major volcanic eruption. So putting those two things aside, what can CAIRT tell us about the kind of background sulfur processes in the budget that might help us to be able to inform, well, policymakers, if they were ever to come to a decision about whether they wanted to do SAI to mitigate warming, surface warming? Thank you.
Thank you. Björn Martin? Sophie?
Yeah, well, I can start. Yeah, thanks for the question. I mean, on the chemistry side, the key, well, one key thing to take away is that the CAIRT will give a full sulfur budget, like you said, and to understand the changing background aerosol layer, we need to understand the sources, like OCS, the strength of the OCS sources, the transport pathways from the troposphere into the stratosphere. And so CAIRT, through the observations of OCS and other minor sources like H2S and so on, will get the flux into the stratosphere, the pathways, and constrain that. So we'll understand why the background may not be returning to as low as we think it should be. So I think from a sort of a more chemical modeling point of view, I think that's one key thing for CAIRT. And then there'd be obviously good sensitivity to sulfate aerosols which are formed from that. So I think it's for me, those are the sort of first things to mention.
Yes, and the other thing to mention is the fact that CAIRT will be able to provide information on other types of aerosol, as I mentioned, by injection of a wildfire aerosol, for example. So it will be able to really provide a detailed picture of what are the aerosol in the stratosphere and the amount of aerosol in the stratosphere. So this will be also very important.
No, I just would like to add, we didn't talk much about chemistry here at all, but there is a lot of information in CAIRT data on chemistry. For example, we have essentially the full nitrogen species budget, and volcanic eruptions in the past have shown to change the partitioning of the nitrogen family, affecting ozone chemistry. So these are all things that can be studied also with the CAIRT product, although we haven't put that here into the foreground. Yeah.
Okay. Next question. Maybe there at the back, and then here in front, and then over there.
Good morning, thanks for the presentation. Juan Añal from the University of Vigo. I am also the head of an international team commissioned by the International Space Science Institute to check the impacts of climate change in the upper and middle atmosphere. I have a couple of questions. The first one is, we have known just a few days ago that NASA has ordered to take out the Time Saver sensor satellite, and we are not going to have anything to measure long-term climate there anymore. So I wanted to know how CAIRT could some way work on this and help to improve our monitoring of climate change there. The other one is related to a different issue. We have just known recently that atmospheric mercury is being processed in the stratosphere. So half of the mercury that is now deposited on Earth's surface and affecting fisheries is going through the lowermost stratosphere. This is extremely important because it is transported from tropics to polar regions and oceans in less than 1 year. I wanted to know if CAIRT could help to track their masses that are carrying all this mercury through the lowermost stratosphere, which I think is extremely important. Thank you very much.
Okay, so the key point to remember here is that there will be a necessary gap of several years before CAIRT, EE11 Explorer launches in the 2030s. So that's built into the system. But in terms of those trends in the upper atmosphere and low frequency variations, CAIRT will inform on those in terms of circulation, in terms of what you've already heard, in terms of NOI, but also some of the wave driving that would infer these sorts of circulation changes. So in terms of the transport trend type of answer to your question, it will inform, but will take time to build up those necessary observations that take time to build up trend information.
Yeah, and a quick point also. I mean, we have all worked with Sabre. We have seen what we could do better, and CAIRT is partly a product of that.
Bernd.
Regarding the middle upper atmosphere, just want to add that CAIRT has definitely the potential to provide important information for data assimilation, also for systems looking at space weather. So space weather models would definitely benefit from this data. As already started from Sabre data, and unfortunately will be disrupted in the near future.
Okay, I believe there was a question just here and then over there. Yeah, if we can start here, thank you.
Aurélien Poglagen, still Laboratoire de Météorologie Dynamique. So you have shown that CAIRT will be able to measure aerosol particles and water vapor, but your backup slides brought me one question. Will it be able to measure ice particles and ice microphysical properties? This is a very important question for science, but also for climate impact of cirrus clouds, and there are still questions around ozone depletion in polar stratospheric clouds.
Do you want to start, Björn Martin, and maybe we hand over to Michael?
Yeah, we can do that. CAIRT builds on the heritage of the MIPAS instrument, and with MIPAS we have shown that not only ice measurements were possible in the stratosphere or in the UTLS region, but also information on isotopes. But I would like to use this opportunity to pass this question on to my colleague Michael Höpfner from KIT, who has worked quite a lot on this topic.
Yeah, thanks, Björn Martin. Sorry for that. We have worked, there was a big study on ice and other aerosol retrievals in the past, an ESA study, and we have shown that if the ice clouds are thin, optically thin, which are these ultra-thin cirrus or the polar stratospheric clouds, if they are thin, we can deduce, under some assumptions, we can deduce microphysical properties, like this kind of size distributions. Yeah, and we can distinguish between ice. Of course, this is in the infrared, clear that we can distinguish between ice and other kind of particles. So there will be the possibility, not for extremely thick cirrus clouds. Also, this is clear, they are optically thick, but for the thin cirrus clouds, we have a lot of information. Yeah.
Thank you, Michael, and then maybe here on my right-hand side. Oh, sorry. Oh.
And so I think really what we do now is just go to a small number of selected online questions that have been coming in over the last hour or so.
Okay.
And my suggestion is the Q&A started 5 minutes late, so if we go to 12:55, if that's okay, so we've got 10 minutes for online questions. Yeah, right. Okay, 6 minutes. 6. Yeah. So as I say, we've got a lot of online questions, and what we're trying to do here is just select ones that haven't really been touched on at all with the previous questions, and kick off in chronological order with those. And the first one is from Susan Tegtmeier. She's from University of Saskatchewan, and it's particularly related to CMIP forcing datasets. And so her question is, there's a large interest in moving to regular and sustained delivery mode of historical forcing datasets for CMIP models, or for CMIP exercises rather, and she wants to know how CAIRT measurements might be able to contribute to the regular delivery of updated and expanded forcing data sets, and ideally near real time?
Yeah, okay, so thank you for this question. We had a dedicated slide in our presentation looking at what particularly could be done in terms of data sets which could go into CMIP forcing data sets. So there are quite a few of them. One is related to volcanic stratospheric aerosol. We have seen the observations which directly link to that. So this is an important contribution, particularly because CAIRT observations provide the full sulfur budget, which is important for constraining these forcing data sets. Similarly, ozone is an important forcing data set, but here this is mostly relying on model simulations. Nevertheless, these model simulations need to be validated, need to be compared to observations, and their CAIRT, of course, will contribute definitely. Then we have solar forcing, where energetic particle forcing is also a part. NOY is well, it even goes directly into these data set in forms of upper boundary conditions. So then there are a lot of opportunities to directly compare forcing data sets to observations, thinking about biomass burning emissions. I'm also thinking about anthropogenic emissions. And then we have greenhouse gases, of course, where CAIRT will definitely contribute with methane and N2O. And CFCs, of course.
Okay, we'll move on. We won't be able to address all of these questions in the time we have, so we'll carry some of these over to the discussion at the end of the day, where we have another hour. We've got two questions from Hanley Liu, who's from NCAR, so we're covering, I don't know how many different time zones here, but they're in Colorado, so it's pretty early in the morning for them. The first science goal specified in the presentation is how the middle atmosphere circulation is changing. Will the design mission life be long enough to achieve this goal? Point one. Has there been forward modeling studies to demonstrate that the trend in circulation, temperature, and tracer species could be extracted from the variabilities in measurement noise? You showed some plots that had sort of decadal variability in them, so I think this is an important question.
Yeah, in the interest of time, I give a short answer. Yes, we have used that in the formulation of the requirements that we say on the 100-kilometer scale, less than half a year lifetime, and we said, I didn't mention that here, the requirement for zonal averages less than quarter of a year, and that should be sufficient to detect interannual variability and also trends on the time scale of the mission.
Okay, probably the last one that we have time for the lunch break. This is from Thomas Berner, who is Professor of Theoretical Meteorology, University of Munich. Current climate models show very large moist biases in the lowest stratosphere. Could you say something about how CAIRT may help to constrain water vapor, and in particular, its temporal and spatial variability in this region, where observational data coverage is currently sparse?
Yeah, I try to actually in my presentation. I mean, it's not only in climate models, it's also in weather prediction models. There the answer is even simpler, because the assimilation of CAIRT data will directly correct this. In climate models, there's also this bias. Now, by better characterizing the bias with CAIRT observation, one can work towards better models. One could also think about data assimilation, but it's essentially that road where the CAIRT data with better precision and higher resolution across the tropopause will help on a range of models.
And of course, with the high 3D capabilities, we see also the STE going on, and that should also help.
So I think we will close the Q&A with this. I have one recommendation for the questions that are coming in, also for CAIRT maybe, because we have still a 1 hour open question and answer slot at the end of the day. But if the people online can try to make their questions as concise as possible. That would really help us in identifying, say, the ones that we would like to bring forward. So this would be, say, a little request from the online participants.
Thank you so much.
Thank you.
So with that, we conclude the morning session. There is lunch. Time to regenerate. And it's around the corner, yes. So we start back again sharply with WIVERN at 1400. Thank you very much.